Hello and welcome back. This is the video series about Qt containers in Qt 5 and Qt 6. I'm Giuseppe. In this video, we're going to explore the sequence containers in Qt. So, what are the sequence containers in Qt? Well, Qt has different classes that you can use as a sequence container, but the two most important ones by far are QVector and QList. So those are the two that we will be focusing on in this video. In an upcoming video, I'm going to show you a little bit about the others that are available in Qt. For now, let's start talking about QVector and QList, and we're going to see both in Qt 5 and Qt 6 how they work and what's their behavior from a, if you want, higher level point of view. I would not like to go into each and every API call and each and every function of these two classes because they're very similar, and because if you know one sequence container from the C++ standard library from Qt, you pretty much know them all. They have a very similar set of functionality. However, how this functionality is exactly implemented is the key part here. So let's focus on that instead. So the first class that we're going to discuss is QVector, and specifically QVector in Qt 5. We're going later to see what's changed in Qt 6. And what is QVector in Qt 5? Well, it is the direct counterpart of standard vector. What do I mean by that? It's a container that, yes, it's got implicit sharing and all the Qt goodies on top of it, but in a nutshell, it offers you constant time, random access inside its contents. These contents are stored contiguously in memory, just like an array. All the elements are packed together, and this gives you some interesting properties when it comes to speed, when it comes to compatibility with C APIs, and so on. For instance, as you can expect, since all the elements are kept contiguous in memory, it means that you can have a very fast iteration on both directions. This kind of data structure is extremely cache-friendly. And also, since they're kept contiguously, you can pass a pointer and asides to the elements themselves to, say, an API that wants these, that doesn't want to know what a vector is. Okay, so when to use it? If you just need to store a sequence of elements, a sequence of objects, QVector should be your default choice. Just like standard vector is pretty much the default choice in the C++ world. How does a QVector look like in memory? It looks pretty much like the diagram, which is on this slide. As you can see, QVector is, as I said, just a pointer. It points to its pimple. Inside the pimple, you've got reference counter, some bookkeeping, and the elements, which are contiguous in memory. But as you can see, there is some leftover extra capacity, which is possible to have at the right end. And this gives you some ideas about what are its algorithmic complexities when it comes to the operations that manipulate the vector itself. That is, inserting an element somewhere into the middle costs you a possibly linear number of operations. That's because you have to make room for that element, and that means moving all the elements to the right of it further down the road. But if you're just appending at the end, and if you're lucky and if you got extra spare capacity, then that appending at the end is actually very cheap. It costs you cost and time. If, however, you run out of capacity because your vector is full, then it means that you need to reallocate the whole payload, the whole pimple. That means allocating a bigger chunk of memory. That means moving the elements over, and therefore that cost is at least linear, plus, of course, the cost of memory allocation involved. Removal, just like insertion, it's pretty much for free if you remove at the rightmost end, but if you remove from the middle, it costs you a possibly linear number of moves because you will need to compact the vector by moving elements from the right end down. Now, these are, if you want, the behaviors that you would expect from any vector-like implementation, but as I'm saying these, don't rely precisely on these behaviors. The reason is some of these behaviors at least have changed in Qt 6, may change again. This has to do with the trend that I mentioned some time ago in an earlier video in this series. Qt may tune these behaviors from time to time in order to accommodate some use cases, and therefore strictly depending on these particular properties when you're using these containers, may backfire in the sense that your applications may regress in algorithm complexity if you are relying on these behaviors and Qt changes them. That was QVector, pretty easy. Now let's focus on the other one, which is QList. And the name QList is a pretty misleading name. From time to time, people still think that QList looks like a list, so it should be like a linked list of nodes or something like that. But no, QList is nothing but that. What is actually QList? QList is an array-backed random access sequential container with constant time access. Wait a minute, isn't that a vector? Well, almost. QList looks a little bit like a vector, but it's a vector of something strange. But first and foremost, let's discuss this. This is not a linked list, okay? This is actually an array of something. An array of what, precisely? A QList does not necessarily contain your elements. What a QList does, really, is to manage an array of pointers. So, to be more precise or more exact, what a QList really manages is an array of cells. Okay, an array of fixed size, empty cells. Each cell has the same size of a pointer on your platform. And what do I do with those cells? I mean, I've got an array, but where do I put my data? Well, where do you put your data exactly depends on your data. That is, depending on the type that you put inside a QList. If you have a QList of ints, or a QList of strings, or a QList of images, a QList is going to behave in two different kind of ways, and that depends entirely on the nature of the data type that you want to put in. QList can act in one or two different ways. In the first case, a QList can hold inside those cells pointers to the objects that you're storing inside the list, and these objects get individually heap allocated. So you're going to allocate a new object somewhere in memory, and the QList itself inside those cells is going to hold pointers to these objects. In the second mode, those cells are going to hold the elements themselves. And since the cells have always the same size, always the size of a pointer, what happens if your elements are smaller than a pointer? Maybe they're char, and your pointer is void star on 64-bit platform is 64 bits. So those cells will have some extra padding because the cells themselves never change in size. Now these cells are organized as an array. So they are contiguous in memory. And this specific array also has some empty room, just like QVector, but in the case of QList, this empty room is actually on both extremities. So there is some extra space at the beginning for an optimization for prepend, and some extra space at the end as an optimization for appending elements. So let's now analyze the first way in which QList can work in Qt 5, the so-called array of pointers mode. Given a QList, and this QList is storing objects of a type T, and the type T is either bigger than the size of a pointer on your platform, meaning that objects of type T do not fit into the QList cells. Or if the type T that you have is something which is not relocatable, and that means that objects of type T cannot be moved in memory by means of mem copy, then the way QList works is that it's still an array of cells, but these cells are going to contain pointers to objects of type T. The objects that you add into the list, for instance here, this object A, object B, object C, when you insert them into the list, they're going to get individually heap allocated, and the pointer that you get when you insert these elements in are going to be stored into the array of cells. Now, there are important couple of things here to underline. The first is that this is not an array of pointers as far as your code is concerned. When you have a QList of T, you still have a plain container. You don't see that there is an indirection happening behind the scenes. This is all dealt with in a completely transparent way. It's just how QList works internally. It's data structure organization, if you want. The second thing is that what do I mean exactly that T must be relocatable? How does QList know if a given data type, maybe a data type that you have defined, is relocatable or not? And the way this works is by using type traits. You need to declare that a given
type T, that maybe you're defining yourself, is relocatable for QList to know about it. By default, QList is not going to assume that a type is relocatable unless it's told so. And this is interesting because effectively it means that this strategy, the array of pointers strategy, is the default strategy of QList for user-defined data types, unless, again, you do something extra, unless you tell QList that your type can be moved in memory. The other thing is that, of course, the size of your data type T must fit into the cells. So if you have a data type T, which is simply bigger than a pointer, and when you think about it, it's really, really easy to have such a type T, right? As soon as you have a pointer and something else, a pointer on the sides or something along those lines, a pointer in a B table or something along those lines, then you're already exceeding the size of a pointer on your platform. Then, of course, QList is going to use these particular allocation strategy, because otherwise your elements are not going to fit into the cells.
Alternatively, QList can work in a very different way. That is, if you got a data type that is small enough to fit, so the size of T is smaller or equal than the size of a pointer on your platform, and also T is marked with this special type trait to be relocatable, then QList will avoid the extra heap allocations for your elements. What QList is going to do is to store the elements of type T directly into that backing array. So in this sense, it may look like it's behaving like a vector, like something that stores elements in a contiguous way in memory, just with some extra padding at the left and right. But that's not actually true. As I mentioned, there may be padding inside that backing array because the cells are still the size of a pointer. So if your A, B, C are strictly smaller than a pointer, there is padding, and so this is not actually compatible with a vector. An interesting note here is that if you consider the Qt5 value classes, what's the common characteristic of them? Well, we should know by now the Qt5 value classes are all implicitly shared. Also our Qt6 value classes, but there is a difference there. What does this mean? It means that value classes in Qt5 have the same size of a pointer, because that's all they are. And a class in Qt5 is just a pointer pointing to the dynamic allocated payload for which implicit sharing takes place. That means that these classes actually fit directly into QList, so for those, QList avoids the double indirection that you would have in case QList had to heap allocate each Qt5 class individually. Now, I know what you're thinking. You're probably thinking something like, this sounds complicated. I mean, you got a data type that the QList in this case, and depending on the type of the list, it behaves in different ways and whatnot. And what's the deal with these heap allocations, etc., etc., etc. Of course, there is a trade-off. Of course, this was done with something in mind. And the idea here is that QList in Qt5 and Qt4 also was designed this way for a specific purpose. The purpose is to minimize the code size expansion of such a class template over its row speed. Why is that? Well, that has to do with the fact that when you manipulate a QList, when you insert elements, when you remove elements, and so on, the management of that array can be done in a completely type-erased way. That is, that array is always, as I said, an array of cells, so an array of void star, and that array is actually resizable by calling realloc. It may take a little while to understand that this is true, but it is. And so this means that the entire code that has to deal with the management of that backing array is completely type unaware. It's type erased. And it makes it possible for that code to limit its size in terms of code expansion, because you don't need any specific properties of your type T when you manage that array. So that's nice. Okay. The other part, however, is that doing one allocation per element in case QList is working in array of pointers mode is definitely expensive. You wouldn't think that adding 100 doubles into QList is going to cause 101 memory allocations, would you? Well, it does, or at least it does on some platforms. And so That, of course, is the deal breaker here, and it's the reason why QList is very much frowned upon inside Qt, and also outside Qt, inside the Qt community. And that's why I mentioned that QVector should be your default choice of a Qt container and not just QList. And what's more, this double nature of QList behavior is definitely surprising. It's not something easy to explain, especially if you're a newcomer to Qt and you should understand, okay, look, there's this container, and this container changes behavior depending on data type you put in. And that's already strange enough. But also knowing in advance what kind of behavior you're going to get depending on data type. If I give you a QList of QImage, a QList of QString, a QList of QStringView, which behavior you're going to get from each and every of these data types? It's not easy to say, even for me, and I use Qt the entire day, and I've been using Qt for some 20 years now. So I don't like the idea that people should overthink this, and that's why I suggested QVector should be your default choice as a Qt sequence container. And add on top the fact that if you change between 32 and 64 bits, the QList behavior may change, so you may go from array of pointers mode to vector-like mode, and or you may get waste of space in case the element you're putting in is smaller than the cell size. This really makes the QList situation kind of not too good. Yeah, let's try to avoid it. Unfortunately, of course, QList is the container which is exposed all over the place by Qt. When you call any Qt API and that API returns a list of something, you'll be pretty sure that that something is a QList. So this gives us a little bit of tension in the Qt API, right? There is this container QList. We don't like it. We'd like to move away from it, but at the same time, it's used all over the place. And if you're really concerned about performance or stuff like that, well, then rest assured, QVector in Qt 5 is also faster than QList in Qt 5. The reason for that is that compilers got better with time. So while QList design made perfect sense in a world where compilers were not that good at optimizing instantiations of class templates, today's compilers have no such problem. So QVector code is actually optimized quite efficiently, and therefore you should be using QVector no matter what. Yes, there are a couple of exceptions to this rule. There are a couple of specific operations in which QList can still outperform QVector, but these operations are so uncommon that I would say you shouldn't really be optimizing for those. It definitely sounds strange. So things like insertions at the front, that's because QList has a little bit of extra space at the front, so those operations get faster there. Or if you reallocate and your objects are really, really, really big in memory, a reallocation in that case for QList is simply a little bit of pointer adjustment, while QVector has to reallocate the whole objects. But both of these can be solved, either by choosing a better container than QVector, than a vector, if you really plan to do a lot of insertions in the front, so things like a deck come to mind. And also, if you do have this problem of having gigantic objects, then it would make sense to be more explicit in your API and, for instance, use a vector of unique pointers if that's if that's your cup of tea. So what is the future for QList and QVector in Qt 6? I should not say future, probably present, because Qt 6 has already been released. So what do you find in Qt 6 when it comes to these two classes? Well, when Qt 6 started its development, there were a few goals set for these two classes, and in particular for QList. What we wanted to do was to, on one side, improve QList's performances. That is, stop with all these shenanigans of having individually heap allocated objects. Let's try to do what QVector does, because that's by far the easiest way to approach how to build a sequence container that also gives good performances. So can we do that? Can we use QVector's behavior rather than QList's behavior? Well, sure, we could just, do a massive search and replace all over inside Qt and rename QList to QVector and move on. But that would be terrible, because that would break all the client code using Qt. Now you have functions that returns QList, and those functions would change signature to return QVector, and your code will be affected by this terrible source break. So we wanted to avoid that at all costs. There are also APIs in Qt that have the name list in API, so things like get children list or whatever. We wanted to avoid renaming them into children vector or something like that, because that again is a source break. We don't want source break for kind code. And also finally, perhaps stop teaching and stop explaining all this mess about QList's double behavior. So what happened in Qt 6? Well, eventually, all these set of considerations led to a decision. That is, in Q6, we still have QList, we still have QVector, but QList is now an alias to QVector. So the type is still there for you to use, but now it just becomes or behaves like a QVector. Between us, that's not true. Technically, what happened is that QVector is now an alias to QList, and QList implementation has been redone to be like a vector. Okay, that's not important. That's just a little distinction. The important bit is that both containers, QList and QVector, refer to the same container, which is a vector-like container in Qt 6. And of course, while this decision is probably for the best and the future of Qt, it is still not entirely painless in the sense that there is a number of small incompatibilities that you may face. For instance, if you upgrade your existing code, your existing applications using Qt 5, and you want to upgrade them to Qt 6, there are a couple of corner cases in which this upgrade may hit you. Again, this is just in case you're doing something in a corner case. I don't want to be the guy who says, oh, this is all terrible. So keep this slide as good advice in terms of things to look out for. Thankfully, they're not that common to do, and therefore your upgrade process can be completely painless. But in case it is not, take a look at this. The first thing to be aware of is this. In Qt 5, you may have a QList, and you may have a QList working in the so-called array of pointers mode, meaning that each element is individually allocated on the heap. So the memory layout of your list will look something like this. You have your list, it's a pointer, there is some bookkeeping data, and then the actual array of cells, and then each element is on the heap. As if you want a side effect or a corollary of this particular construction in memory is this. Your elements, A, B, C, once they are inside the list, and kept alive of course by the list, those elements are never again moved around in memory. That is, what happens if you have that list and you insert some extra element? Then what you're going to do is shuffle the pointers, you're going to modify the backing array, but the elements themselves don't move. They're individually heap allocated. What's going to move is the pointers to them. Okay, so as long as those objects themselves are alive, as long as you don't erase them or destroy them from the container, those are immutable in memory if you want, or immovable, should say. They're mutable, you can modify them, but they don't move in memory. And what is the consequence of this? A consequence of this is that any reference or any pointer to these objects is always valid, as long as the list itself keeps the object alive. So as long as you don't destroy the list or erase the object from the list, the object is alive in memory. And this is important. Why is it important? Because as a side effect, you may accidentally depend on this behavior. That is, you may have some little piece of code which keeps a reference to some object inside the list and then tries to manipulate the list. Maybe it inserts new elements. Maybe it changes the order of the elements. It doesn't matter. But this can happen, and this has happened, personally, to me at least once. This becomes a problem in Qt 6. Why is that? Because this behavior, this particular keeping the integrity of references, to use a very fancy term, only works when QList is working in this array of pointers mode. Since in Qt 6, QList behaves like a vector, there is no longer array of pointers, there is nothing like that, and therefore you no longer have integrity of references when you modify the list. You have it only in some very controlled scenarios. For instance, if you insert after the current position and you don't reallocate, there is a very stricter number of conditions to satisfy to keep integrity of references in Qt 6. In the general case, this got broken. Now, thankfully, this doesn't happen every day. Thankfully, this is quite rare, but I cannot say that this never ever happened to me. So it's definitely something to watch out for, and especially if you see strange crashes or strange behaviors, please run your application under address sanitizer, memory sanitizer, under Valgrind or any similar tool to be able to spot that you may have some illegal memory access somewhere inside your program. And finally, there is a second thing which may break for you, that now depends. That is, in order not to regress code that in Qt 5 was relying on the fast prepend of QList in Qt 5, then QList in Qt 6 also has the same prepend optimization. That is, it has the same empty space at the beginning and empty space at the end kind of design. But this now has an implication. And the implication is this, that since QList and QVector in Qt 6 are the same class, it also means that QVector now has a prepend optimization. And this may break code in the very rare case that you may assume that you're not reallocating anything if you're inserting elements while being under capacity. So if you have a vector and you ask it, what is your capacity? Oh, it's 1000. And what's your current size? Oh, it's 500. Okay, then I can push back elements to you and I will not reallocate. Well, that's not now strictly true in Qt 6. And that's because those extra capacity may be a little bit at the beginning, a little bit at the end, and you don't know which side you have capacity, or for which side you have capacity. And therefore, you may end up reallocating no matter, even if you're under capacity, simply because you reached one limit of the container. There is a workaround in place that fixes, let's say, 99% of the most common cases, which is this one. If you do reserve extra capacity, this extra capacity is reserved only at the end, and only at the right end, I should say. And the idea for that is pretty simple, is that because people typically reserve just before doing some sort of loop in which they push back elements, that is, in which they put elements at the right end of a vector. So when that happens, Qt will do the smart thing and only reserve right capacity and leave left capacity unused. Sure, that's a possibility, but still in the general case, I cannot tell you that this code will work in all cases. You may be very, very unlucky. And once more, try to use memory sanitizers, try to use Valgrind to spot that there is something wrong there. However, to say it all, this is very hard to spot in terms of correctness. You won't have likely illegal memory access. You may just have performance regressions here. That is, an insertion that you thought was going to happen in constant time now may happen in linear time. And so some algorithmic code, I would say, may behave strangely or may downgrade their performances. And this could be the reason. So watch out for this and know that QVector in Qt 6 has this slightly different behavior. Okay, that's all I have for you now. In the next video, we're going to treat the associative containers in Qt 5 and Qt 6. So thank you very much for watching. Don't forget to subscribe to get notified when we publish more content like this. And as usual, have a good day.